Alright, so time for a new kind of inference, and that is inference not so much for the mean, which we've been focusing on quite extensively lately, but inference instead for a population proportion. So, sometimes we're interested not in doing inference on a mean, but instead in doing inference on a population proportion, right? So there's lots of examples of when this might be the situation. One such example is we might be interested in the proportion of voters that favor a bill, or the proportion of voters that, say, favor a certain candidate. We might be interested in the actual probability, the actual percent chance that a particular surgery or technique will be successful, or from a quality control standpoint or a quality control perspective, we might be interested in, say, the percent of all products that are defective. Now, interesting observation. Probably the most commonly used type of confidence interval that we ourselves see on a not entirely daily basis, but a regular basis, is a confidence interval for proportions, right? Every election cycle, we see all over the news, we see all over the newspapers, right, that the percentage of voters that favor Barack Obama is somewhere between 52 and 57%, right? The proportion of voters who say they would vote for Hillary Clinton is somewhere between, say, 49 and 53%. That is, right, when the newspapers are giving us these types of intervals, when the newspapers are giving us these probabilities, these proportions, what they're really doing, right, how they're actually calculating these numbers is they're doing confidence intervals, right? So we in fact, a confidence interval perhaps seems a little strange or foreign, but what I'm trying to say, which I think is pretty neat, is it's something that we actually see, as I said, fairly regularly. So, just as the sample mean is the best guess for the true mean, the sample proportion is our best guess for the true proportion, right? The sample percent is the best guess for the true percent. The sample proportion is denoted P with a little hat on it, right? We called that P hat. P hat is defined as R over N, where R is the number of successes and N is the size of our sample. So it's the number in our sample that satisfy the characteristic or interest over the size of the sample. That gives us, of course, the percent of the sample that satisfies the characteristic of interest. So, for example, if 300 out of 500 voters are against the death penalty, then our P hat would be 300 over 500, which would be 0.60 or 60%. Our best guess for the percent of all voters that are against the death penalty would be 60%. Example 2. Let's say that we come up with a new surgery, a new process, a new procedure. To figure out how effective it is, we would of course have to actually try it out on some patients. Let's say that we do a program where we do a trial, we enlist 100 patients. Of the 100 patients that actually take the surgery, it's successful on 20 of those patients. So our P hat would be 20 over 100, or 20%. Note, just like before, the probability that P hat actually equals P is very close to 0. The probability that our sample proportion is actually the true proportion of interest, it's very close, it's virtually impossible. Nonetheless, it is quite likely that P hat will be very close to P. Just like before, just like when we were talking about the sample mean and the true mean, we can quantify this idea of closeness with a confidence interval. A confidence interval for a proportion for a certain confidence level C is given by the following formula. Again, it's a very similar looking formula. It's our best guess, which is P hat, plus or minus a margin of error. The margin of error is still just a certain number of standard deviations out. We have the critical value, which, going back to our first confidence interval, is based on a z distribution or a normal distribution. and it's times that standard deviation of p hat, which in this case is going to be the square root of p hat times 1 minus p hat divided by n. How do we do this on a calculator? Well, just like the last two confidence intervals. We go to the stat menu, we hit the stat button, we go over to test, we go down, 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 way downtown, we go past z interval, past t interval, I think we go a few more down, and you should see something 1 prop z int, because it's just one proportion, and it's a confidence interval that has the letter z. The critical value is based on a z distribution. So, we'll actually do two examples. The first one, let's do a 95% confidence interval for example 1. Example 1 was, right, the percent of people that are against the death penalty. So, how do we do that? Well, here's our 1 prop z int. You can see there's not a lot that we need to fill in. We have to fill in the x, the n, and the confidence level. We said 95% confidence, so I put 0.95 in. Our sample size, our n, was 500. Now the x. The x is not a percent. The x is not p hat. It's important that you know that, important that you remember that. The x, what the calculator wants, is the number of people that satisfy that characteristic of interest. It's the r from our p hat formula. So in this example, that's 300. So we plug that into our calculator, we go down to calculate, we hit enter, and there's the actual interval. The actual interval is, right, from 55.7% to 64.3%. So we would say this. We would say that we are 95% confident that the true proportion of voters who are against the death penalty is between 55.7% and 64.3%. Could an interval of uncertainty, right, could narrowing it down to that range of values be helpful to us? Well, sure. Imagine if we're a politician or a political advisor, and we're wondering whether we should bother spending our time and our resources trying to push through a bill or a legislation that say is heavily related to a person's opinion on the death penalty. And the type of people we think that would be for our bill are the types of people who are against the death penalty. Maybe it's some kind of anti-death penalty bill. And we're interested in whether or not we think a majority of voters are going to be sympathetic to it. Well, this confidence interval, right, does tell us. It says, we don't know. We don't know what percent of voters are going to be against the death penalty. We can't know that unless we sample all voters. Nonetheless, right, our entire range of values, our entire interval is over 50%. So that leaves us feeling rather confident that no matter what that percentage is, it's more than 50%, hence a majority. Alright, another example. Let's go ahead and make a 90% confidence interval for example 2. Example 2 was the percent or proportion of successful surgeries. So again, we have to fill in the information. We had 100 patients. Of those 100 patients, 20 of them had a successful surgery. We were asked to do a 90% confidence interval, so we put 0.9 there. Here's our output. So our confidence interval is somewhere between 13 and 26%. We would say that we are 90% confident that the true probability of a successful surgery is between 13 and 26, perhaps 27%. Right, which is worth keeping in mind because, right, if we have whatever ailment it is that we're talking about here, and if we went to see a doctor and the doctor suggested this surgery, maybe it's an eye correction surgery, the doctor will likely quote that it has a 20% chance of being successful. That is, the doctor will give what's called the point estimate. It's the sample proportion. But in reality, there's a lot more uncertainty than what the doctor's letting on. At the 90% confidence level, the actual percent chance that the surgery could be successful could actually be as low as 13%, or, right, if you want to be an optimist, could be as high as 27%. That is, there's an entire range of values or range of probabilities that often doctors do not disseminate to their patients.
So let's encapsulate what we talked about with a broad overview. At this point, we've learned how to do 3 different types of confidence intervals. Any one of these 3 is not very difficult. The calculator does the heavy lifting for us. So what is the challenge for us on a homework, or perhaps even more importantly on an exam? The challenge for us is trying to decide which of the 3 should we be using. Should it be that z int? Should it be that t int? Should it be the 1 prop z int? So there are 3 different types of confidence intervals we've talked about in the order that we've talked about. And we started with the confidence interval for the mean when the population standard deviation was known. We went on and made the observation that in practice, the population standard deviation is almost never known. And so a sort of more practical confidence interval is one that uses the sample standard deviation. That's our t interval. That's that number 2. And then we talked about a confidence interval for a proportion. So in terms of our decision flowchart, when we're reading a word problem on a test, and we're trying to decide which of these 3 we should be using, the flowchart first is a decision. Is it a confidence interval for a mean, or is it a confidence interval for a proportion? Now, a lot of times you can look for that buzzword, percent or proportion, and that tells you that you're doing a confidence interval for a proportion. But that's not 100% perfect strategy. Ultimately, what does it boil down to? Well, it's pretty cool because it comes full circle, way back to the beginning. In our first lecture, we talked about experimental units and variables. And to really pick, with no pun intended, a high level of confidence, the appropriate confidence interval, the first question you should be asking yourself is, what is my experimental unit? Once you've nailed that down, you need to be asking yourself, what is my variable? And then finally ask yourself, does this variable take 2 outcomes or more than 2 outcomes? If the variable only takes 2 outcomes, you're doing a confidence interval for a proportion. If it takes more than 2 outcomes, you're doing a confidence interval for a mean. Let's think about it. So what's the example we just did? The example we just did was the surgery example. In that case, our experimental units were patients. And the variable was, well, for every patient, either their surgery was successful or not successful. That's 2 outcomes. Hence a confidence interval for proportion. What was the example before that? We had a bunch of voters. Every voter was either for or against, that was the variable, was their opinion on the death penalty. That opinion only had 2 outcomes. They're either for or against it. Hence a confidence interval for a proportion. Now, what were some of our examples from previous PowerPoints? Well, we did one where we were looking at how long it took to complete a test, right? In that case, our experimental units was what? Exactly, our experimental unit was a student. And what was the variable? The variable was, for every student we recorded, how long did it take that student to finish their exam? Now, in terms of how long it takes to finish an exam, that could take any number of outcomes, can't it? Right? 50 minutes, 51 minutes, 59.24 minutes if we measured it precisely enough. Now, why is this important? Because I could throw you a trick question. What if I asked you to do a confidence interval for the percentage of fat in yogurt? A particular brand of yogurt. We might see that buzzword, percentage of fat. We might jump to a confidence interval for a proportion, but we'd run into a brick wall, right? Because again, what's our experimental unit? An experimental unit would be a cup of yogurt. What's the variable? A variable is the percent of yogurt in that cup, or percent of fat in that yogurt. And the percentage of fat could be a whole bunch of different values, right? It could be 1%, 2%, 3%, 3.749%. It could be pi percent. Ah, that'd be nice. Pi percent yogurt. So do we see that it's not always as easy, it's not always as black and white, it's just looking for the word percent. And it is a nice illustration of why some of those basic building blocks that we talked about way back